Welcome to Sleeping Researcher, your gentle companion in the world of science narration, designed to help you drift into restful sleep. Here, we explore fascinating scientific ideas with calm and soothing words, inviting your mind to relax and wander in peaceful curiosity. Today, we begin a quiet journey into a concept that lies at the heart of the universe itself: entropy. Often described as a measure of disorder or randomness, entropy may seem like a force of chaos. But what if it is also the ultimate engine of creation? What if, within the slow unfolding of entropy, the universe finds its way to build complexity, life, and endless new beginnings? As we explore this delicate balance between order and disorder, we will uncover how entropy shapes everything from the smallest particles to the vast cosmos. We will gently examine how this fundamental principle in physics guides the dance of energy and matter, quietly powering the processes that bring about change and transformation. Before we begin, if you enjoy this calming exploration, please consider liking the video and subscribing to Sleeping Researcher. Your support helps us continue to bring peaceful scientific stories that soothe the mind and inspire wonder. Now, let us settle in and softly open the door to entropy's subtle, creative power. Imagine a force so subtle, so deeply woven into the fabric of reality, that it quietly orchestrates the unfolding story of the cosmos. This force is known as entropy, a concept often associated with disorder and decay, yet it holds a much richer and more profound role in the grand scheme of existence. Entropy, in the language of physics, measures the number of ways a system can be arranged, reflecting the natural tendency of things to evolve from order toward a state of greater probability, often perceived as disorder. But beneath this apparent chaos lies a dynamic engine, tirelessly driving the transformation and evolution of matter and energy throughout the universe. It is this hidden engine that propels change, fuels the complexity of life, and underpins the ceaseless dance of creation and destruction that shapes everything we observe. At first glance, entropy may seem like a force of decline, a herald of eventual heat death and universal quietude. Yet, when viewed through a deeper lens, entropy reveals itself as a fundamental driver of innovation and emergence. In thermodynamics, entropy explains why heat flows from hot to cold, and why certain processes are irreversible. However, this irreversible flow also opens pathways for new structures and patterns to form. For example, stars, planets, and even living organisms arise because of local decreases in entropy, which are balanced by increases elsewhere. This interplay creates pockets of order in a vast sea of growing disorder, suggesting that entropy is not merely a measure of decay, but a catalyst for creative complexity. By embracing the natural push toward equilibrium, entropy quietly encourages the universe to experiment with new forms, fostering diversity and novelty. microscopic scale, entropy governs the behavior of atoms and molecules, guiding chemical reactions that build the very molecules of life. The random motion of particles and the countless possible arrangements they may adopt give rise to the rich tapestry of chemical complexity. In biological systems, entropy drives metabolic processes, enabling cells to harvest energy and maintain order within themselves. Far from being an antagonist, entropy facilitates the flow of energy that sustains life and allows it to flourish. This perspective invites us to see entropy not as a villain of cosmic decline, but as an essential partner in the ongoing narrative of growth and transformation. It is through this lens that we begin to appreciate entropy as a fundamental engine propelling the universe forward in its endless journey of creation. Furthermore, the concept of entropy extends beyond physical systems into information theory, where it measures uncertainty and the amount of information. Here, entropy becomes a bridge between the physical and the abstract, linking the tangible universe with the intangible realm of knowledge and communication. The increase of entropy in information systems mirrors the thermodynamic principle, underscoring a universal tendency toward complexity and change. This unifying thread hints at a profound truth. Entropy may be the underlying mechanism driving not only physical transformation, but also the evolution of ideas, structures, and even consciousness itself. As we delve deeper into this understanding, entropy emerges as an ultimate engine, quiet, relentless, and immensely creative. As we explore the universe through the lens of entropy, we begin to uncover a narrative where chaos and order are not opposing forces, but partners in an intricate dance. The subtle push toward equilibrium fosters the emergence of new forms, guiding the cosmos from simplicity to complexity, from the birth of stars to the rise of life. Entropy acts as a catalyst, shaping the continuous process of creation that defines our reality. This perspective invites us to rethink entropy not as a force of destruction, but as a vital engine of transformation, quietly powering the unfolding story of the universe. With this understanding, we are ready to explore how entropy's creative power manifests in the structures and phenomena around us. When we first encounter the term entropy, it is often associated with disorder, chaos, or the inevitable decay of systems. This interpretation, while rooted in everyday experiences, such as a messy room or a crumbling structure, only scratches the surface of what entropy truly represents in the realm of physics. At its core, entropy is a measure of energy dispersal within a system, describing how energy spreads out and becomes less available to do work. Rather than simply denoting randomness or destruction, entropy reveals the direction in which natural processes evolve, guiding energy from concentrated forms into more diffuse states. This subtle shift in perspective allows us to appreciate entropy as a fundamental principle that governs the flow and transformation of energy throughout the universe. It is through this lens that entropy moves beyond mere disorder and becomes a descriptor of the intricate balance between energy concentration and dissipation, setting the stage for the emergence of new patterns and structures. The concept of entropy invites us to look deeper into the mechanisms that drive change on all scales, from the microscopic to the cosmic. In thermodynamics, entropy quantifies the number of ways a system can be arranged while maintaining the same energy state. This multiplicity of configurations points to a natural tendency for systems to evolve towards states with greater possibilities for energy distribution. Yet, within this evolution lies a paradoxical creativity. As energy disperses, it can trigger self-organization and complexity. For example, the heat emitted from a star radiates into space, increasing entropy overall, but simultaneously fuels the formation of planets and the conditions necessary for life to emerge. Thus, entropy is not merely a harbinger of decay, but a dynamic engine that orchestrates the transformation of energy, enabling the birth of order within the unfolding chaos. By embracing this nuanced understanding, we begin to see entropy as a bridge between the dissolution of old forms and the genesis of new ones. It is important to recognize that entropy does not act in isolation, but within the context of the laws of thermodynamics, particularly the second law, which states that the total entropy of an isolated system can never decrease over time. This principle underlines a universal arrow of time, one that moves forward as energy spreads and systems evolve toward equilibrium. Yet within open systems, such as our planet or living organisms, local decreases in entropy are not only possible, but essential for growth and complexity. These pockets of decreased entropy are made possible by the input of energy from external sources, such as the sun, which drives processes that build and maintain intricate structures. This interplay of entropy increase globally and local decreases in complexity reveals the subtle and profound role that entropy plays as an engine of creation, enabling life and complexity to flourish amidst the broader trend toward energy dispersal. In this light, entropy becomes a guiding principle that balances the forces of change and stability in the universe. As we refine our understanding of entropy, it becomes clear that its role extends far beyond a simple measure of chaos, encompassing the very processes that foster innovation within the cosmos. The dispersal of energy not only drives systems toward equilibrium, but also lays the foundation for new forms of order to emerge spontaneously. This phenomenon, observed in everything from chemical reactions to the formation of galaxies, demonstrates how entropy can serve as the ultimate engine for creation, catalyzing transitions that generate complexity from simplicity. The universe, seen through this lens, is a vast dynamic tapestry woven by the flow and transformation of energy, where entropy guides the threads from one pattern to the next. Such a perspective invites us to embrace entropy as a fundamental force of transformation, quietly shaping the unfolding story of existence. At the heart of our universe lies a law as unyielding as time itself, the second law of thermodynamics. This principle tells us that in any natural process, the total entropy, often described as the measure of disorder or randomness, will always increase or remain constant in an isolated system. It is not merely a scientific rule, it is a profound statement about the direction in which time flows and how energy transforms. Entropy's inevitability means that energy spontaneously disperses, moving from concentrated states toward more diffuse configurations. This gradual spreading is not chaos without purpose, but rather a universal propensity toward equilibrium, a balance of energies that shapes every physical and chemical process. From the cooling of a hot cup of tea to the vast cooling of stars, entropy governs the irreversible march towards states of higher probability and less free energy. This fundamental law applies everywhere, transcending scale, from microscopic particles to entire galaxies, reminding us that the universe is perpetually evolving, carried forward by the unrelenting tide of entropy. Yet, the increase of entropy, often associated with decay and disintegration, paradoxically fosters the conditions for creation and complexity. As energy flows and disperses, it drives systems away from uniformity, setting the stage for new structures to emerge. For example, when energy moves through matter, it can trigger chemical reactions that form molecules of increasing complexity, eventually leading to the intricate processes of life. Similarly, on a cosmic scale, the gravitational collapse of gases, governed by thermodynamic principles, results in the birth of stars and the formation of planetary systems. This interplay between energy dispersal and the formation of ordered structures reveals entropy not as a force of mere destruction, but as a subtle engine that facilitates transformation. These emergent phenomena arise not in spite of entropy, but because of it, guided by the second law's imperative. The universe self-organizes in fascinating and often surprising ways. Such insights invite us to reconsider entropy as a creative principle, woven through the fabric of natural processes. From the perspective of physics, entropy's relentless increase is intimately tied to the concept of time zero, giving a direction to change and evolution. This temporal asymmetry means that while microscopic laws of physics are reversible, the macroscopic world we observe is defined by irreversible transformations governed by entropy. Each moment is a step forward in this unfolding progression, where energy gradients drive matter and information into new arrangements. These gradients are the engines powering the universe's dynamic complexity, enabling transitions that lead to order emerging from apparent disorder. In living systems, for instance, energy from the sun flows through biological networks, increasing local order while contributing to the overall rise in entropy across the cosmos. Such processes demonstrate that the second law does not forbid complexity, but rather requires it to exist within a broader context of growing entropy. This understanding deepens our appreciation of entropy as an essential force shaping the creative evolution of the universe. The universality of entropy's influence extends beyond physics into the realm of information and organization. In information theory, entropy quantifies uncertainty and the amount of information contained within a system. Similarly, natural systems use the flow of energy and the increase of entropy to process information, adapt, and evolve. For example, ecosystems and the weather exhibit complex behaviors arising from the continuous exchange and dissipation of energy. These phenomena highlight how entropy drives the spontaneous emergence of patterns and structures that are both stable and flexible. The second law, therefore, does not merely describe an end state of disorder, but rather the ongoing journey of transformation, where energy's dispersal fuels the perpetual creation of novelty and diversity. This perspective encourages us to view entropy as a source of dynamic creativity, rather than mere decay or randomness. As we continue to explore these ideas, we find that entropy is deeply intertwined with the processes that sustain life and the broader cosmos. At the heart of the physical universe, entropy serves as the guiding principle behind the transformation and flow of energy. It is through the gradual increase of entropy that energy moves from concentrated, usable forms toward more dispersed and less accessible states. This flow is not a mere decay into chaos, but rather a fundamental driver of change that enables the universe to evolve. When energy transitions from one form to another, be it from sunlight captured by plants to the warmth radiated back into space, entropy governs the efficiency and direction of these processes. The second law of thermodynamics tells us that in any natural transformation, the total entropy of an isolated system will increase, ensuring that energy spreads out over time. This spreading is what powers the engines of creation, allowing structures and patterns to arise within the constraints of physical law. Without entropy, energy would remain static and unchanging, and the dynamic dance of matter and energy that underpins existence would cease. In this way, entropy is the unseen force that enables the continual renewal and reshaping of the cosmos. Consider how stars, planets, and even living organisms emerge from this entropic flow. Stars ignite when clouds of gas collapse under gravity, releasing tremendous energy that then radiates outward, increasing the entropy of their surroundings. The warmth from stars drives planetary atmospheres and oceans, creating environments where complex chemistry can flourish. On Earth, life itself thrives by harnessing the energy flow from the sun, converting low-entropy solar energy into biological work, while releasing higher-entropy heat into the environment. This constant exchange maintains the delicate balance necessary for ecosystems to develop and sustain themselves. Entropy, therefore, is not just a force of dissolution. It is the framework within which energy gradients can be exploited to build intricate, self-organizing systems. Each step in these processes, from the fusion reactions in stellar cores to the metabolic pathways within a cell, relies on energy dispersal governed by entropy. The universe's capacity to create complexity and order is intimately linked to this fundamental principle. deeper level, entropy acts as the universal clock that dictates the direction of time and the possibility of change. Because entropy tends to increase, it gives rise to irreversible processes that move the universe forward. This arrow of time allows systems to evolve from simple beginnings into more elaborate forms, as energy flows and disperses through various channels. Within this temporal framework, entropy enables the spontaneous formation of new structures, from galaxies to neural networks, by driving energy through pathways that favor emergence and complexity. The interplay between energy input, entropy production, and system organization creates a delicate balance where innovation can unfold naturally. In this sense, entropy is not an obstacle, but a catalyst. It fuels the continuous cycle of breaking down and building up that characterizes the cosmos. The creative power of entropy reveals itself in the persistent emergence of novelty and adaptation across scales, reminding us that the universe thrives on transformation and energy flow rather than stasis. This understanding invites us to see entropy as a profound engine for creation rather than mere decay. The study of entropy also extends into the realms of complexity science and thermodynamics, where it helps explain how ordered structures coexist with the overall trend toward disorder. Open systems, such as Earth's biosphere, maintain local decreases in entropy by importing energy and exporting entropy to their surroundings. This energetic balance allows life and complex phenomena to persist and evolve over time. The continuous flow of energy, driven by the increase in entropy outside these systems, acts as a sustaining force, preventing stagnation and enabling adaptation. Such dynamics highlight how entropy is not simply a measure of disorder, but a fundamental principle that orchestrates the flow of energy in ways that foster creativity and resilience. By appreciating entropy's role as the universe's workhorse, we can better understand the delicate interplay between chance and necessity that shapes all natural processes. This perspective deepens our insight into how the cosmos continuously generates diversity and innovation through the persistent movement of energy. As we explore further, the concept of entropy reveals itself as a cornerstone for understanding the engines that drive creation across the universe. At first glance, entropy is often understood as a measure of disorder, a relentless force guiding the universe toward chaos and decay. Yet, this perspective only tells part of the story. In many natural systems, the increase of entropy paradoxically coincides with the emergence of new structures and patterns. This seeming contradiction arises because entropy does not simply denote randomness. Rather, it quantifies the number of possible configurations a system can explore. As systems evolve, they may traverse from less probable, highly ordered states to more probable ones that nevertheless exhibit intricate order on different scales. This interplay between disorder and order is especially evident in open systems, environments that exchange energy and matter with their surroundings. These systems harness the flow of energy, driven by entropy gradients, to organize themselves into complex forms. Such phenomena challenge our intuitive ideas and invite us to reconsider entropy not as a harbinger of destruction, but as a creative engine capable of birthing complexity from chaos. One of the most profound illustrations of entropy's creative power is found in biological systems. Life on Earth thrives by exploiting energy disparities, importing low-entropy energy from the sun and exporting higher-entropy energy back to space. This flow enables organisms to build and maintain highly ordered structures, cells, tissues, organs that would otherwise be improbable in a closed system. The continuous increase in entropy outside the biosphere provides the thermodynamic impetus for life to develop and evolve. Far from being a passive backdrop, entropy actively shapes the pathways through which living systems adapt and innovate. The principles of non-equilibrium thermodynamics reveal that far from equilibrium conditions, maintained by energy fluxes, are essential for the emergence of self-organization and complexity. In this way, entropy acts as a guiding force, orchestrating the dance between energy and matter that underpins the genesis of life and its sustained diversity. This dynamic relationship between entropy and life underscores a universal theme that creation often springs from the very processes that seem to herald disorder. Beyond biology, the creative potential of entropy extends into physical and chemical systems, where spontaneous pattern formation arises from thermodynamic principles. Examples such as convection cells in heated fluids, crystalline growth, and chemical oscillations demonstrate how energy flow and entropy production can give rise to ordered spatial and temporal structures. These emergent phenomena, often described as dissipative structures, exist precisely because of the continuous dissipation of energy that increases entropy in the surrounding environment. Without the drive toward equilibrium, these patterns would not sustain themselves. This insight reveals entropy as a fundamental engine of innovation, capable of transforming uniformity into complexity through natural processes. Far from a mere measure of decay, entropy facilitates the spontaneous generation of order within the constraints of physical laws. Such understanding invites us to perceive entropy as an indispensable architect, shaping the architecture of the universe's evolving tapestry. On a cosmic scale, entropy's paradoxical role continues to inspire profound reflection. The expansion of the universe and the thermodynamic arrow of time both point toward increasing entropy. Yet, within this grand march, galaxies, stars, and planetary systems emerge. These structures concentrate matter and energy into ordered states, creating environments where complexity can flourish. The gravitational clumping of matter, fueled by the underlying thermodynamic processes, illustrates how entropy can drive organization on vast scales. Each local pocket of order is sustained by the broader context of increasing entropy, a cosmic dance between chaos and structure that has persisted for billions of years. This dance reveals that entropy is not merely a destination, but a journey, one that propels the universe toward ever new forms of creation and transformation. By embracing entropy's dual nature, we open ourselves to a deeper appreciation of the ongoing creative processes that shape our cosmos. Ultimately, the concept of entropy invites us to shift our perspective, seeing it not as an antagonist to order, but as a fundamental mechanism that enables complexity and innovation. The continuous flow of energy and matter, driven by entropy gradients, acts as a universal engine for creation, fueling the emergence of life, the birth of structure, and the evolution of the cosmos itself. This profound insight bridges physics, chemistry, biology, and cosmology, revealing a unifying thread woven throughout the fabric of nature. As we continue to explore entropy's paradoxical role, we find ourselves at the threshold of understanding how the universe perpetually crafts new patterns from the interplay of chance and necessity. This realization paves the way for the next chapter in our journey, where we delve deeper into the mechanisms by which entropy shapes complexity across scales. At the heart of this fascinating interplay between entropy and order lies the concept of dissipative structures, introduced and extensively studied by Nobel laureate Ilya Prigogine. In traditional thermodynamics, entropy is often understood as a measure of disorder, a tendency for systems to move toward equilibrium and randomness. Yet, Prigogine's groundbreaking work revealed that in open systems, those exchanging energy and matter with their surroundings, entropy can paradoxically foster the emergence of new, ordered states. These dissipative structures arise precisely because the system is driven away from equilibrium by continuous flows of energy. Rather than collapsing into chaos, such systems self-organize, creating patterns and structures that are maintained by the ongoing dissipation of energy. This insight challenges classical views and offers a deeper understanding of how complexity naturally arises in the universe. Imagine a river flowing over rocks, shaping intricate patterns in the sand below. This is a simple natural example of a dissipative structure. The flow of water, an energy gradient, continuously reorganizes matter into ordered ripples and formations. In a similar way, biological systems, planetary atmospheres, and even galaxies can be seen as vast dissipative structures, constantly exchanging energy and matter with their surroundings. Prigogine's work, mathematically and experimentally, demonstrated how these systems maintain their order and structure far from equilibrium, driven by entropy-producing processes. The continuous production of entropy, rather than being destructive, becomes a creative force, enabling systems to evolve, adapt, and maintain their complexity. This turns the conventional narrative of entropy on its head, inviting us to see disorder as a source of dynamic stability and innovation. The implications of dissipative structures extend deeply into our understanding of life's origins and the evolution of complexity. Living organisms are quintessential examples of open systems that sustain themselves by importing energy and exporting entropy to their environment. This continuous energy flow supports the intricate molecular machinery within cells, allowing them to grow, reproduce, and adapt. Prigogine's framework helps explain how life manages to sustain and increase order locally, despite the universal trend towards entropy increase. It reveals a profound truth. The very processes that drive the universe toward disorder simultaneously provide the conditions necessary for the emergence of order, creativity, and life itself. This dynamic balance between energy flow and entropy production forms the backbone of natural evolution across all scales. Beyond biology, the principles of dissipative structures illuminate phenomena in physics and cosmology, where systems far from equilibrium spontaneously develop new, complex patterns. From the swirling storms of Jupiter's atmosphere to the large-scale structure of cosmic filaments in the universe, the ongoing interplay of energy flows and entropy production acts as a creative engine. Prigoghine's insights give us a scientific framework to understand how the cosmos itself is not simply winding down into heat death, but is continually generating novel forms and structures. This perspective enriches our appreciation of the universe as a dynamic, evolving entity, where the arrow of time points not only toward decay, but also toward innovation and emergence. As we continue this exploration, the concept of dissipative structures invites us to reconsider many natural processes as manifestations of entropy-driven creativity. It opens avenues for understanding the intricate dance of order and disorder that shapes phenomena from chemical reactions to ecological systems and even social dynamics. Prigoghine's pioneering work lays a scientific foundation for this view, demonstrating that the engine of entropy is not merely a force of destruction, but ultimately one of creation and renewal. This understanding leads us naturally to consider the specific mechanisms by which entropy governs complexity across different scales, preparing us to delve deeper into the fascinating ways nature harnesses disorder to build order. At first glance, entropy might seem to be a simple measure of disorder, a tendency toward chaos and decay. Yet, within living systems, entropy reveals a far more intricate and dynamic role. Biological organisms exist as open systems, constantly exchanging energy and matter with their surroundings. Metabolism, the complex set of chemical reactions that sustain life, is a prime example of entropy in action. Through metabolic processes, organisms intake low-entropy energy in the form of nutrients and sunlight, and dissipate higher entropy heat and waste products back into the environment. This continuous flow of energy and entropy enables cells to maintain their internal order, repair damage, and grow. Rather than a passive slide into disorder, entropy here becomes a driving force that sustains life by facilitating the transformation and redistribution of energy. Beyond individual organisms, entropy also plays a vital role in the grander scale of evolution. The emergence of complexity in biological systems, new species, ecosystems, and intricate biochemical pathways is deeply intertwined with entropy production. Evolution can be viewed as a process where life explores countless configurations, some of which harness energy more efficiently or adapt more successfully to their environment. Each of these adaptations contributes to a net increase in entropy in the larger environment, even as they create pockets of highly ordered structures within organisms. This balance between local order and global disorder exemplifies how entropy drives the creative forces of natural selection and diversification. Thus, entropy is not an antagonist to life, but a fundamental partner in its continual unfolding and innovation. The concept of dissipative structures, as introduced by Ilya Prigogine, further illuminates how entropy underlies biological complexity. These structures maintain their organization by exporting entropy to their surroundings, effectively using disorder to sustain order. From the rhythmic beating of a heart to the self-assembly of proteins, living systems rely on this delicate exchange to function and evolve. It is through this entropy-driven metabolism and regeneration that life manages to defy the simplistic notion of inevitable decay, instead embracing a dynamic equilibrium where creation and destruction coexist. Such processes demonstrate that entropy is not merely a measure of chaos, but a fundamental engine propelling the continuous renewal and creation of life itself. As we observe the entropic engines at work within biology, we begin to appreciate how deeply intertwined the laws of thermodynamics are with the essence of existence. The flow and transformation of entropy provide the energetic foundation upon which the diversity and resilience of life are built. From microscopic cells to vast ecosystems, entropy guides the emergence of patterns, the adaptation to changing conditions, and the persistence of life through time. This perspective invites us to see life not as an exception to the natural order, but as one of its most profound expressions, where entropy acts as the ultimate architect of creation, constantly shaping and reshaping the living world. At the heart of the natural world's complexity lies a remarkable process that beautifully illustrates the dance of entropy and order: photosynthesis. In this elegant mechanism, plants and certain microorganisms capture the radiant energy of the sun and convert it into chemical energy stored within intricate organic molecules. This transformation is, in essence, a local reduction of entropy, a movement from simpler, less organized forms of energy, such as sunlight and carbon dioxide, into highly structured, energy-rich compounds like glucose. It is a delicate balancing act, for while the immediate environment within the plant becomes more ordered, the overall entropy of the universe continues to increase, in keeping with the second law of thermodynamics. This interplay reveals how life cleverly navigates thermodynamic constraints to forge complexity out of simplicity, turning sunlight into the building blocks of all terrestrial ecosystems. Delving deeper Photosynthesis can be seen as a quintessential example of entropy serving as an engine for creation rather than mere decay. The process begins when chlorophyll molecules absorb photons, exciting electrons and initiating a cascade of energy transformations. These energy exchanges power the synthesis of carbohydrates from carbon dioxide and water, molecules that are themselves products of previous entropic processes in the environment. The plant's cells orchestrate these reactions with exquisite precision, channeling disorder into the assembly of complex molecular structures. This not only sustains the plant's own growth, but also provides nourishment for countless other organisms. In this light, photosynthesis exemplifies how living systems harness the gradients of entropy to build and maintain order, revealing the subtle artistry of nature's thermodynamic choreography. The implications of photosynthesis extend far beyond the individual plant, as it forms the energetic foundation of nearly all life on Earth. By converting sunlight into stable chemical forms, plants create reservoirs of usable energy that flow through food webs, supporting the growth and reproduction of animals, fungi, and microorganisms alike. This continuous flow of energy and matter embodies the principle that while entropy tends to increase universally, local pockets of reduced entropy can emerge and persist through energy input and transformation. Such pockets of complexity are the crucibles from which biodiversity arises, shaped and sustained by the fundamental thermodynamic forces. Photosynthesis, therefore, is a luminous example of how entropy fuels the ongoing creation and evolution of life's intricate tapestry. As we reflect on the elegant simplicity and profound significance of photosynthesis, we come to appreciate that entropy is not merely a force of disorder and decay. Instead, it is also an engine of transformation, enabling the emergence of order and complexity from the universe's vast potential. Through the continuous flow of energy from the sun, photosynthesis demonstrates the capacity of living systems to harness entropic gradients, creating structured forms that sustain life and inspire wonder. This perspective invites us to view entropy as a creative force, one that underpins the natural world's ceaseless innovation and growth. When we consider entropy in the realm of physics, it is often described as a measure of disorder or randomness within a system. Yet, this seemingly simple concept holds profound implications for the emergence of life itself. In a universe governed by thermodynamic principles, entropy does not merely signify decay or chaos. Instead, it acts as a powerful driver of change, pushing systems toward new configurations that can sometimes appear remarkably ordered. The delicate balance between entropy and energy flow creates opportunities for chemical reactions to become more complex. In the primordial conditions of early Earth, countless molecules interacted within energy gradients, leading to the spontaneous organization of matter into increasingly intricate structures. These processes suggest that life may not be an improbable anomaly, but rather a natural outcome of entropy-driven chemical dynamics. At its core, the emergence of life can be viewed through the lens of non-equilibrium thermodynamics. Living organisms maintain their structure and function by continuously exchanging energy and matter with their surroundings, effectively managing entropy production. This balance allows them to sustain ordered states temporarily, despite the universal trend toward greater entropy. Theories in this field propose that life's origin was a consequence of systems seeking pathways to dissipate energy more efficiently. Complex molecular assemblies, such as early self-replicating molecules or protocells, could have arisen because they offered new routes for energy dispersion. This perspective enriches our understanding of life not as a defiance of natural laws, but as a harmonious expression of them, where entropy serves as the ultimate engine, propelling chemical creativity and complexity. The interplay between entropy and energy flow also extends to the concept of autocatalysis, where certain molecules catalyze their own formation, creating feedback loops that enhance complexity. Such mechanisms may have been crucial in the transition from simple chemistry to the earliest forms of metabolism. In this view, entropy drives the formation of dynamic, self-sustaining networks of reactions that grow more elaborate over time. These networks can harness energy gradients, converting them into organized chemical work that fuels further molecular innovation. As a result, the emergence of life can be seen as a natural progression of matter evolving to maximize entropy production on a larger scale. This dynamic process underscores the creative potential inherent in thermodynamic laws, revealing entropy as both a force of transformation and a foundation for biological complexity. In exploring these ideas, we begin to appreciate the subtle beauty in how physical laws shape the natural world. Entropy, often misunderstood as a mere harbinger of disorder, instead reveals itself as a fundamental engine driving the universe toward new forms of organization. The origin of life, from this thermodynamic vantage point, emerges not only as a scientific mystery, but also as a testament to the universe's capacity for self-organization under the influence of energy flows and entropy gradients. This understanding invites us to look deeper into the molecular dance that shaped the dawn of life, where chaos and order coalesce into the first sparks of biological existence. We now turn our attention to the ways in which such principles continue to influence living systems today, linking the past with the ongoing story of life's evolution. When we cast our gaze upward into the vastness of the cosmos, we see not only the grandeur of stars and galaxies, but also the quiet work of entropy shaping their very existence. At first glance, the concept of entropy, often defined as a measure of disorder or randomness, might seem at odds with the breathtaking order found in celestial formations. Yet, it is precisely through the unfolding of entropy that the universe orchestrates the emergence of these complex structures. In the primordial clouds of gas and dust scattered throughout space, gravitational forces gather matter, and as particles collide and interact, energy is redistributed. This energy flow, governed by the inexorable increase of entropy, leads to the concentration of matter into denser regions, setting the stage for the birth of stars. Here, entropy acts not as a mere agent of decay, but as a subtle engine that drives matter from diffuse chaos into concentrated, radiant bodies that will illuminate the cosmos for billions of years. As a star ignites within its cloud, nuclear fusion begins to convert hydrogen into helium, releasing vast amounts of energy in the process. This transformation marks a profound interplay between order and disorder. The star maintains a delicate balance, resisting gravitational collapse through the outward pressure generated by fusion, while continuously radiating energy into the surrounding space. In this ongoing exchange, entropy increases globally as high-energy photons escape and heat the cosmic environment. Yet locally, within the star, a highly organized state persists. The life cycle of stars, from their formation to their eventual demise, whether as white dwarfs, neutron stars, or black holes, reflects the complex dance of entropy shaping matter and energy. Each stage represents a shift in how energy gradients are harnessed and dissipated, fostering new possibilities for cosmic evolution. Beyond individual stars, entropy also governs the grander scale of galaxies. Immense collections of stars, gas, and dark matter bound together by gravity. These colossal systems evolve over billions of years through interactions and mergers, driven by the redistribution of energy and matter. Entropy manifests in the gradual spreading and mixing of cosmic material. Yet, it simultaneously enables the formation of intricate galactic structures, spiral arms, dense cores, and vast interstellar clouds. The complex gravitational choreography within galaxies is a testament to how entropy fosters diversity and complexity, even amid the overarching trend toward equilibrium. By connecting the microscopic processes of particle interactions with the majestic scale of cosmic structures, entropy reveals itself as a unifying principle that links the smallest constituents of matter with the vast architecture of the universe. In contemplating the role of entropy in cosmic evolution, we come to see it as more than a measure of disorder. It is a profound driver of transformation and creativity on a universal scale. The gradual increase of entropy propels energy through gradients, enabling matter to coalesce, stars to shine, and galaxies to dance through the cosmic night. This ongoing flow of energy and matter, shaped by the laws of thermodynamics, creates the conditions for complexity to emerge from simplicity. As we trace these processes from the formation of atoms to the birth of stars and beyond, we glimpse the deep interconnection between the microscopic and the cosmic, a continuum where entropy weaves the fabric of creation itself. As we delve deeper into the cosmic interplay of entropy, black holes emerge as some of the most fascinating and enigmatic players in this grand thermodynamic drama. These celestial phenomena, born from the collapse of massive stars, serve as ultimate sinks for matter and energy, drawing everything within their grasp into an abyss from which nothing, not even light, can escape. Yet, contrary to their reputation as mere cosmic devourers, black holes reveal a profound connection to entropy, embodying a paradoxical balance between destruction and information. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking revolutionized our understanding by proposing that black holes possess entropy proportional to the surface area of their event horizons. This insight suggested that black holes are not just gravitational traps, but thermodynamic entities governed by laws akin to those of ordinary heat engines. The vast entropy encoded on the event horizon implies a deep link between gravity, quantum mechanics, and information theory, hinting at an underlying order beyond the apparent chaos of matter disappearing into darkness. The concept of black hole entropy introduces a new dimension to the idea of information loss in the universe. Traditionally, entropy is viewed as a measure of disorder or the number of microscopic configurations consistent with a system's macroscopic state. In black holes, this measure takes on a more abstract form, representing the information about all the matter and energy that has fallen past the event horizon. This raises profound questions. How is this information stored, and does it ever truly vanish? The famous black hole information paradox challenges the classical notion that information is irretrievably lost, suggesting instead that the universe preserves information in subtle, encoded ways. Hawking radiation, a slow leakage of particles from black holes, hints at mechanisms through which information might escape, connecting thermodynamics with quantum processes. Thus, black holes do not merely consume, they transform, acting as cosmic crucibles where the conventional rules of physics blend and evolve. This interplay between entropy, gravity, and quantum mechanics deepens the mystery of how the universe manages complexity and order within seemingly chaotic extremes. Contemplating black holes as thermodynamic systems invites us to reconsider the very engines that drive creation in the cosmos. The immense entropy associated with black holes suggests that they are repositories of vast amounts of information, encoded on their event horizons in ways that challenge our understanding of space and time. This holographic principle, emerging from the study of black hole thermodynamics, proposes that the information content of a volume of space can be represented as encoded data on its boundary surface. Such a principle hints at a universe where the fabric of reality itself is woven from information, and entropy is the measure of its unfolding complexity. In this light, black holes might be viewed not just as sinks, but as transformative engines, where extreme conditions catalyze the emergence of new physical laws and structures. They symbolize a boundary between known and unknown realms, urging us to explore how entropy and information guide the evolution of the cosmos on scales both vast and minute. Beyond their gravitational dominance, black holes serve as remarkable laboratories for the unification of fundamental forces and the reconciliation of classical and quantum physics. The thermodynamic properties attributed to black holes suggest that entropy is more than a passive record of disorder. It is an active participant in the universe's ongoing narrative of creation and transformation. As matter spirals inward, its information content becomes encoded in the black hole's entropy, intertwining with the fabric of space-time itself. This process challenges our intuitive notions of permanence and loss, hinting at deeper symmetries and conservation laws that govern the cosmos. The study of black hole entropy pushes the boundaries of our understanding, suggesting that the ultimate engines of creation are not only the energetic processes we observe in stars and galaxies, but also the subtle, information-rich dynamics hidden within these cosmic enigmas. Such reflections invite us to consider entropy not as an end, but as a continuous thread weaving complexity from the depths of darkness. The holographic principle emerges from the interplay between gravity and quantum mechanics, proposing a profound relationship between entropy, information, and the very fabric of space-time. In essence, it suggests that all the information contained within a volume of space can be represented on its boundary surface, much like a hologram encodes three-dimensional details on a two-dimensional plane. This idea revolutionizes our understanding of entropy, transforming it from a mere measure of disorder into a fundamental currency of reality. Entropy, in this context, becomes deeply linked to information theory, where the quantum bits of data stored on a boundary surface dictate the state of everything enclosed within. Such a perspective hints that the universe itself might be a vast informational construct, where the growth of entropy corresponds to the unfolding of cosmic complexity. As this principle gains traction, it offers a new lens through which to view creation, not as a linear unfolding of matter and energy, but as an emergent phenomenon arising from encoded information at the edges of existence. The relationship between entropy and information becomes even more compelling when considering black holes as physical embodiments of the holographic principle. Black hole horizons, the surfaces that define the limits of no return, appear to store information in a way that defies classical intuition. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon, suggesting that information is fundamentally two-dimensional in nature. This discovery bridges the chasm between the macroscopic laws of thermodynamics and the microscopic rules of quantum mechanics, revealing that information and entropy are inseparable and foundational to space-time geometry. The encoding of information on these horizons may be the universe's way of preserving the integrity of quantum states, preventing information loss, and allowing creation to proceed without contradiction. In this light, entropy acts as both a ledger and an engine, recording the history of interactions while simultaneously driving the emergence of new structures in the cosmic arena. Beyond black holes, the holographic viewpoint extends to the very cosmos we inhabit, suggesting that the universe's expansion and evolution might be understood through the lens of information dynamics and entropy. If space-time itself emerges from more fundamental informational building blocks, then the growth of entropy is not simply a march toward chaos, but a process that seeds new realms of possibility and complexity. This conceptual shift invites us to reimagine the arrow of time and the genesis of order as intertwined aspects of a universal narrative encoded at the boundaries of space-time. In this framework, entropy is not a destructive force, but a creative one, facilitating transitions between quantum states that manifest as particles, fields, and ultimately, the large-scale structures we observe. The holographic principle thus reframes the relationship between disorder and information, positioning entropy as the ultimate engine driving the ceaseless birth and transformation of reality itself. As scientists delve deeper into the connections between entropy, information, and geometry, new mathematical frameworks arise to capture these subtle relationships. Quantum entanglement, a phenomenon where particles share states across distances, appears to play a key role in stitching together the fabric of space-time, with entropy quantifying the degree of this interconnectedness. The holographic principle suggests that space-time and gravity emerge from patterns of entanglement encoded on a lower dimensional boundary, where entropy measures the complexity of these quantum links. This insight points to a universe where creation is the unfolding of intricate information networks, governed by principles that blend physics, computation, and geometry. Understanding how entropy governs these networks could reveal the mechanisms by which the cosmos continually generates structure, complexity, and life. In this unfolding story, entropy transcends its classical interpretation and becomes the driving force behind the universe's dynamic tapestry. Entropy is often portrayed as the harbinger of decay, the inevitable march toward disorder and dissolution. Yet, this perspective reveals only a fraction of its profound role in the cosmos. At its core, entropy measures the multiplicity of possible arrangements within a system, reflecting not just randomness, but potential. When energy flows through natural systems, entropy guides transformations that lead not merely to breakdown, but to the emergence of new forms and patterns. Consider the gentle spiraling of galaxies, or the branching networks of rivers. These structures arise as matter and energy redistribute, increasing entropy while simultaneously weaving complexity. Nature's dance with entropy is not a surrender to chaos, but an embrace of change, where the increase in disorder paradoxically seeds order on higher levels of organization. In biological realms, entropy plays a subtle yet decisive role in life's creative processes. Living organisms maintain internal order by exporting entropy to their surroundings, effectively harnessing energy gradients to build intricate molecular architectures. This continuous exchange allows cells to grow, evolve, and adapt, turning thermodynamic principles into engines of innovation. Far from negating life's complexity, entropy facilitates it by driving systems away from equilibrium, where non-linear interactions produce emergent behaviors. The folding of proteins, the replication of DNA, and the signaling within neural networks all unfold within this delicate balance. Here, entropy acts less like a force of destruction and more like a sculptor, chipping away at simplicity to reveal the exquisite complexity beneath. Beyond the microscopic, entropy also shapes planetary and ecological systems in ways that foster creativity and resilience. The Earth's climate, for instance, is a vast thermodynamic engine where solar energy input and entropy production create dynamic weather patterns, ocean currents, and ecosystems. These systems self-organize through feedback loops that balance energy flow and entropy generation, producing habitats rich in diversity and adaptive potential. The constant interplay between order and disorder, driven by entropy, encourages novelty and complexity rather than uniformity. This ongoing process implies that entropy is not merely a passive background condition, but an active participant in the unfolding narrative of life and environment. On the grandest scales, the universe itself may be viewed through the lens of entropy as a creative engine. The growth of cosmic structures, from stars to galaxies and beyond, emerges from fluctuations amplified by gravitational forces in an expanding space-time, enriched by quantum entanglement. Entropy here quantifies the hidden information and complexity that arises as these structures form and evolve. Instead of a simple entropic decay, the cosmos exhibits a dynamic interplay where disorder and order coexist in a delicate balance that fosters continual creation. The universal increase in entropy then does not signal an end, but rather a process of transformation, an iterative unfolding of complexity that underlies the very fabric of existence. As we contemplate entropy beyond its classical role, it becomes clear that this principle intertwines destruction with creation, loss with gain, simplicity with complexity. Its subtle guidance shapes everything from quantum phenomena to cosmic evolution, offering a unifying thread that links diverse scales and phenomena. This perspective invites us to see entropy not as a final arbiter of decay, but as a profound driver of innovation throughout nature. In the quiet unfolding of entropic processes, the universe continually crafts new forms and possibilities, revealing creativity embedded within the laws of physics themselves. As we deepen our understanding of entropy's creative potential, new horizons emerge, beckoning us to explore how this fundamental principle orchestrates the ongoing symphony of existence. Entropy, often associated with disorder and decay, reveals a more nuanced role when observed through the lens of complexity theory. At its core, entropy measures the number of ways a system can be arranged, reflecting the inherent uncertainty or randomness present. Yet this randomness does not equate merely to chaos. Instead, it acts as a fertile ground from which intricate patterns emerge. Simple physical laws, when combined with entropic forces, give rise to structures that are both organized and dynamic. Consider the delicate symmetry of a snowflake, formed as water molecules crystallize in response to temperature and humidity fluctuations. Here, entropy enables the transformation from a disordered vapor phase to an exquisitely patterned solid, illustrating how order can arise naturally from underlying probabilistic behaviors. This delicate balance between randomness and order underpins much of the complexity we observe in the natural world. Beyond the crystalline elegance of snowflakes, entropy's interplay with complexity manifests vividly in atmospheric phenomena such as hurricanes. These powerful storms are not just chaotic bursts of energy, they are self-organizing systems driven by the constant flow and dissipation of heat. As warm ocean waters evaporate, energy is transferred and entropy increases. Yet this very increase fuels the spiral formation of the storm itself. The emergent pattern of a hurricane exemplifies how entropic processes can concentrate energy into coherent structures, sustained by continuous exchanges with the environment. In this way, entropy acts as an engine of transformation, guiding the evolution of complex systems that are sensitive to initial conditions, yet remarkably stable over time. Such natural patterns remind us that entropy is not merely about decay, but about the dynamic dance between energy, matter, and information that shapes the world around us. On a broader scale, ecosystems demonstrate the profound relationship between entropy and complexity. Life itself is a testament to this intricate balance, as biological systems continuously consume energy and increase entropy locally, while maintaining highly organized structures globally. Through processes like metabolism and reproduction, living organisms harness entropic gradients, converting energy to sustain themselves and generate diversity. The complex web of interactions in an ecosystem, from microscopic bacteria to towering trees, emerges as a product of countless entropic exchanges. These interactions create feedback loops that foster resilience and adaptability, enabling ecosystems to evolve and respond to environmental changes. Here, entropy serves as both a constraint and a creative force, driving the emergence of rich biodiversity and intricate behavioral patterns. This perspective enriches our understanding of how natural systems maintain order amid the seemingly inevitable tide of disorder. The marriage of entropy and complexity theory also extends into the realm of information, where the encoding and transmission of data reflect similar principles. Patterns within DNA sequences, neural networks, and even social structures arise from the interplay of entropic forces and self-organization. In these systems, entropy governs the potential for variation and novelty, while complexity theory helps explain how stable, meaningful patterns emerge from underlying randomness. This synergy enables the evolution of increasingly sophisticated forms of order, from molecular biology to collective human behavior. By embracing entropy as a generative principle, rather than a mere harbinger of decay, we open new pathways to understand the emergence of complexity across scales and disciplines. It is within this subtle relationship that the universe's capacity for creativity unfolds, hidden in plain sight within the fabric of physical law. In the realm of human technology, the concept of entropy reveals itself as a fundamental force driving both the limitations and possibilities of our inventions. Engines, in their many forms, serve as profound examples of how we harness entropic processes to produce work, transform energy, and ultimately create motion and power. At their core, these machines rely on the transfer and dissipation of energy, guided by the laws of thermodynamics. Entropy, often associated with disorder and decay, paradoxically becomes the catalyst that enables the conversion of heat into mechanical work. This delicate balance between energy input and output, order and disorder, underpins the efficiency of engines. From the steam engine that powered the Industrial Revolution to the modern internal combustion and electric motors that drive today's world. Understanding entropy not only informs the design of these systems, but also pushes the boundaries of innovation, leading to more sustainable and efficient technologies that shape our future. Beyond engines themselves, entropy shapes the broader landscape of human innovation by defining the constraints within which we engineer solutions. Every process of energy conversion entails some degree of energy dispersal, a spread from concentrated, useful forms to more diffused, less accessible ones. This inherent tendency challenges engineers and scientists to devise methods that minimize waste and maximize utility. The evolution of refrigeration, power grids, and even computing devices reflects a continuous effort to understand and manipulate entropy in favor of human needs. By embracing the inevitable rise of entropy, inventors craft systems that channel this natural progression into functional outcomes. For instance, regenerative braking in electric vehicles captures kinetic energy that would otherwise dissipate as heat, converting it back into stored energy. This nuanced interplay between embracing and counteracting entropy fuels a cycle of creativity and refinement, illustrating how the principles of physics become the ultimate engines of human progress. The journey of entropic understanding extends into the microscopic world, where innovations in nanotechnology and materials science reveal new dimensions of energy manipulation. At these scales, entropy governs molecular motion, chemical reactions, and the stability of complex structures. Engineers and scientists harness entropic effects to design self-assembling materials, responsive surfaces, and energy-efficient catalysts. These advancements demonstrate how a deep comprehension of entropy enables the creation of systems that are not only more efficient, but also adaptive and resilient. By aligning technological development with the natural tendencies of energy dispersion, we transcend traditional mechanical constraints and tap into the universe's fundamental creative forces. This synergy between entropy and innovation highlights a profound truth: that the flow and transformation of energy guided by entropic laws are not merely obstacles, but the very engines driving the emergence of new technologies and forms of order. Moreover, the influence of entropy on human technology underscores a philosophical shift in how we perceive disorder and change. Rather than viewing entropy solely as a destructive force, it becomes a source of potential and dynamism. This perspective encourages a more holistic approach to design and innovation, where the inevitable drift toward disorder is embraced as a creative partner. In renewable energy systems, for example, the natural gradients of temperature and light, manifestations of entropic differences, are harnessed to generate power sustainably. Similarly, emerging fields like biomimicry draw inspiration from entropic processes in nature to develop technologies that adapt, self-repair, and evolve. By aligning human ingenuity with the fundamental principles of entropy, we foster a continuous dialogue between the laws of physics and the aspirations of innovation, revealing how the universe's intrinsic tendency toward disorder can be transformed into a wellspring of creation. As we contemplate the role of entropy in engines and innovation, it becomes clear that this concept is not confined to the physical mechanisms alone, but extends into the very mindset that drives technological progress. The recognition of entropy as both a constraint and an opportunity invites us to rethink energy use, sustainability, and the design of systems that coexist harmoniously with natural processes. The future of human technology, therefore, lies in this delicate dance with entropy, leveraging its inevitability while crafting pathways toward greater efficiency and complexity. This ongoing interplay hints at a deeper connection between physical law and human creativity, a connection that continues to inspire new generations of thinkers and innovators. In recent years, the study of entropy has transcended its classical origins, venturing into the enigmatic realm of quantum mechanics, where information and energy intertwine in unprecedented ways. Quantum thermodynamics, an emerging field at the intersection of these disciplines, reveals that entropy is not merely a measure of disorder, but a fundamental currency in the manipulation and transmission of quantum information. Here, entropy governs the behavior of quantum bits, or qubits, which, unlike classical bits, can exist in superpositions of states. The inherent uncertainty and probabilistic nature of quantum systems mean that entropy shapes the potential for information processing and storage at a level previously unimagined. This profound linkage suggests that entropy itself might serve as the ultimate engine driving the creation and transformation of information, a concept that redefines how we perceive the engine of innovation at its most elemental scale. Delving deeper, researchers have uncovered that the flow of entropy in quantum systems underpins the efficiency and stability of quantum computing processes. Entropy dictates not only the loss of information, but also the generation of new, complex states that enable powerful computational abilities. These discoveries highlight that entropy, once seen as a mere harbinger of decay, is instrumental in the birth of quantum coherence and entanglement, phenomena essential for quantum advantage. The subtle balance between order and disorder within quantum states allows for the emergence of patterns and structures that classical systems cannot replicate, positioning entropy as a creative force rather than a destructive one. This shift in understanding opens doors to novel technologies that harness the fundamental unpredictability of nature in the service of design and discovery. Furthermore, the fusion of entropy and information theory in quantum contexts points toward a universal framework where energy, information, and complexity coalesce. Quantum information theory reframes entropy as a measure of uncertainty and potential, guiding how information is encoded, transmitted, and decoded at the smallest scales. This perspective aligns with the notion that the universe itself may operate as an information processing system, constantly generating new configurations through entropy-driven dynamics. By exploring the thermodynamic costs of information manipulation, scientists are beginning to unravel how creation emerges naturally from the interplay between energetic constraints and informational freedom. Such insights suggest that entropy is not simply a physical law, but a profound principle that catalyzes the ongoing evolution of complexity in both the quantum world and beyond. Intriguingly, these breakthroughs also resonate with philosophical reflections on creativity and the nature of existence. If entropy is integral to the generation of novelty within quantum systems, it follows that the principles guiding physical reality may also underlie the processes of innovation and emergence in broader contexts. This convergence offers a poetic vision where the engines of creation are fueled by the very forces once thought to lead only to decay and disorder. The quantum realm thus provides a compelling metaphor for the delicate balance between chaos and order, a balance that sustains the universe's capacity to evolve, adapt, and inspire. As the frontiers of quantum thermodynamics continue to expand, they invite us to reconsider the essence of creativity itself, intertwined with the fundamental laws of nature. At the heart of our experience of time and change lies the concept of entropy, a fundamental principle in physics that governs the progression from order to disorder. Entropy is often described as a measure of randomness or uncertainty in a system, and its natural tendency to increase over time establishes what is known as the arrow of time. This directional flow is not merely an abstract idea, but a concrete aspect of how the universe unfolds. Without entropy's relentless march forward, the distinction between past and future would dissolve, leaving no framework for events to transpire or for anything new to emerge. The very fact that we can remember the past but not the future is intimately tied to this irreversible increase in entropy. It is this asymmetry that allows change to take place, making the universe a dynamic, evolving tapestry rather than a static tableau. Paradoxically, the same force that is often associated with decay and disorder also enables the birth of complexity and creativity. As entropy increases, energy is redistributed and systems move toward equilibrium. But in doing so, they pass through stages of organization that can give rise to new structures. This process can be observed in numerous natural phenomena, from the formation of galaxies and stars to the emergence of life on Earth. Entropy does not simply erode, it reshapes and renovates, setting the stage for innovation within the cosmic dance. The flow of energy through these systems creates gradients, differences in temperature, pressure, or concentration that can be harnessed to do work and build order locally, even as the total entropy of the universe increases. This delicate interplay between disorder and organization forms the very engine that drives creation on all scales, weaving the fabric of existence with threads of both chaos and coherence. In this light, entropy can be seen not as an enemy of life and creativity, but as their indispensable ally. The arrow of time, guided by the increase of entropy, provides a direction towards which systems evolve, enabling processes of growth, adaptation, and transformation. Without this temporal asymmetry, phenomena such as memory, evolution, and even consciousness would be impossible. The irreversible nature of entropy ensures that each moment is unique, with the past receding into memory and the future unfolding as an open canvas. It is within this framework that new ideas, forms, and possibilities can emerge, as the universe continuously explores pathways of increasing complexity. Hence, entropy is deeply intertwined with the potential for novelty, acting as a subtle catalyst for the unfolding of creative processes embedded in the physical world. Modern physics further deepens this connection by revealing how entropy operates not only on macroscopic scales, but also at quantum levels, where the boundaries between order and randomness blur intriguingly. Quantum fluctuations and entanglement contribute to a rich landscape in which entropy is not merely a measure of disorder, but also a resource for information and change. These insights suggest that the arrow of time and the dynamics of entropy are woven into the very fabric of reality, providing the underlying impetus for emergence and transformation. Through this lens, the universe itself becomes a vast, self-organizing system, where the flow of entropy drives the continuous creation of structure, pattern, and life. As we continue to explore these fundamental processes, we find ourselves invited into a profound appreciation of how change is not just inevitable, but essential to the ongoing story of existence. The concept of entropy, traditionally associated with decay and disorder, invites us to reconsider the very nature of creation itself. In classical terms, entropy is often viewed as a relentless force leading toward chaos, a one-way path to an eventual heat death of the universe. Yet, when observed through a broader and more nuanced lens, entropy reveals its paradoxical role as an engine of creation. Rather than merely dismantling structures, the increase of entropy drives the redistribution of energy and matter in ways that foster complexity. This process underlies everything from the formation of stars and galaxies to the emergence of life on Earth. Here, entropy is not an adversary of order, but a fundamental principle that enables new forms of organization to arise from apparent randomness. This reimagining of entropy challenges the traditional dichotomy between creation and destruction. Instead of viewing these as opposing forces, entropy encourages us to see them as intertwined aspects of the cosmic dance. The increase in entropy corresponds to the unfolding of time and the evolution of the universe towards states of higher complexity and diversity. Each step forward in this journey carries with it the transformation of energy gradients into intricate patterns of matter and life. In this sense, entropy acts as a catalyst for emergence, allowing the universe to reinvent itself continually. This perspective invites reflection on existence itself, suggesting that the flow of entropy is not a mere background process, but the very engine that propels the universe's creative potential. Philosophically, entropy encourages a profound shift in how we understand our place within the cosmos. Instead of perceiving ourselves as separate from or victims of inevitable decay, we might recognize our participation in an ongoing process of transformation. Life, consciousness, and even culture can be seen as expressions of entropy's creative force, arising from the interplay between order and disorder. This view honors the fluidity of existence, where stability and change coexist in dynamic balance. By embracing entropy as a source of novelty and innovation, we open ourselves to a more expansive appreciation of reality, one in which creation is not a singular event, but an eternal unfolding. This invites a contemplative stance toward time and change, encouraging acceptance of impermanence as intrinsic to the beauty of life. Beyond the philosophical, the recognition of entropy's creative role resonates deeply with scientific inquiry, prompting questions about the mechanisms that enable complexity to persist amid universal tendencies toward disorder. Exploring these questions leads us toward the frontiers of thermodynamics, information theory, and cosmology, where the boundaries between order and chaos become permeable and dynamic. The universe, through the lens of entropy, appears less as a clockwork machine winding down, and more as a living tapestry, continuously woven from the threads of energy flow and transformation. This evolving mosaic challenges us to expand our understanding of what it means to exist, to change, and ultimately, to create. To appreciate entropy as the ultimate engine of creation, we must first reconsider the traditional notion of entropy merely as disorder or decay. In physics, entropy quantifies the number of ways a system can be arranged, often interpreted as a measure of uncertainty or randomness. Yet, this very characteristic is what fuels the universe's capacity for transformation. As energy flows through different systems, from the microscopic interactions of particles to the vast cosmic structures, the increase in entropy drives processes that unfold complexity rather than simply erasing it. For instance, the warmth of the sun radiating energy outward increases entropy globally even as it enables the blossoming of life on Earth. In this sense, entropy acts less like a destructive force and more like a dynamic engine that propels matter and energy into novel configurations. Delving deeper, the interplay between entropy and information reveals a profound link between physical disorder and the emergence of structured complexity. Information theory, which quantifies uncertainty in terms of bits and data, finds a natural counterpart in thermodynamics. When systems spontaneously organize themselves, such as the formation of intricate molecular arrangements or the growth of biological organisms, it is often through energy dissipation that locally reduces entropy, while the total entropy of the environment still rises. This delicate balance highlights a key insight. Creation is an entropic process where pockets of order arise because the overall entropy budget is satisfied. The universe's capacity to foster complexity, from galaxies to neural networks, is therefore inseparable from the fundamental tendency toward entropic increase. On cosmic scales, entropy continues to be a vital player in the evolutionary narrative. As stars burn their fuel and black holes consume matter, they transform energy and matter, driving entropy ever upward. Yet within these grand processes, new structures emerge: planets, atmospheres, and eventually life, each representing a local decrease in entropy made possible by the vast entropy production of the cosmos. This suggests that the universe is not simply winding down, but is instead engaged in an ongoing creative dance, where entropy's inexorable rise shapes the conditions for innovation and emergence. The flow of entropy is thus a rhythm underpinning the unfolding story of existence, threading together processes that birth complexity from the simplest laws of physics. From the microscopic to the macroscopic, entropy's role as an engine of creation invites us to reframe our understanding of natural processes. It encourages a view that sees the universe not as a place succumbing to inevitable decay, but as a vibrant arena where energy transformations forge new forms and possibilities. The continuous increase in entropy, far from signaling an end, marks a ceaseless impetus for change, adaptation, and novelty. This perspective resonates with emerging scientific frameworks that explore self-organization, dissipative structures, and the complex feedback loops that sustain life and matter in dynamic balance. Entropy, therefore, becomes a guiding principle in decoding the profound question of how complexity arises in a seemingly entropic world. As we contemplate entropy's creative power, it becomes clear that this principle transcends simple categorization as chaos or decay. Instead, entropy embodies a fundamental mechanism through which the universe continuously reinvents itself, balancing the tension between order and disorder. This dynamic interplay challenges us to think beyond static definitions and to embrace a more fluid conception of reality, one in which creation is an ongoing process entwined with transformation, energy flow, and the unfolding potential of matter. As our exploration continues, we move closer to understanding how entropy shapes not only physical phenomena, but the very essence of emergence and existence itself. When we think of entropy, it is often in terms of disorder, decay, or the inevitable march toward equilibrium. Yet, this perspective captures only a fragment of entropy's full significance. In truth, entropy serves as a driving force behind transformation and innovation in the cosmos. As energy disperses and systems evolve, entropy enables new patterns to emerge from the old, fostering complexity rather than mere dissolution. This subtle dance between chaos and order creates a fertile ground where matter and energy rearrange themselves, giving rise to stars, galaxies, and the building blocks of life itself. Rather than being a force of destruction, entropy can be seen as the universe's way of perpetually crafting new forms and possibilities from the interplay of energy and matter. On a deeper level, entropy invites us to reconsider our understanding of time and change. The increasing entropy within an isolated system marks the arrow of time, guiding the universe from simplicity toward complexity. This directional flow is not random, but an essential feature that allows processes of growth and evolution to unfold. Through entropy, simple atoms coalesce into intricate molecules, and these molecules combine to create living organisms capable of adaptation and renewal. The very essence of life is intimately linked to entropy's transformative power, as living systems maintain themselves far from equilibrium by harnessing energy flows and dissipating entropy into their surroundings. In this way, entropy becomes the engine of creation, propelling the ongoing emergence of life and consciousness amid the ever-changing cosmos. Embracing entropy's creative potential also offers a profound philosophical insight into the nature of existence. Rather than viewing the universe as a static structure destined for eventual decay, we can appreciate it as a dynamic process of becoming. Each moment in time is a passage through which energy disperses, matter rearranges, and novel structures arise. entropy underpins this ceaseless renewal, reminding us that creation and destruction are intertwined facets of the same cosmic rhythm. This perspective encourages us to find beauty in impermanence and to recognize that transformation is the fundamental condition of all things. In the grand tapestry of the cosmos, entropy is not a harbinger of endings, but a catalyst for beginnings, inviting us to witness the endless creativity woven into the fabric of reality. As we conclude this reflection on entropy's role in shaping the universe, it is inspiring to see how this principle unites diverse phenomena across scales. From the thermodynamic processes fueling stars to the metabolic cycles sustaining life, entropy links the physical and biological worlds in a shared story of transformation and emergence. Recognizing entropy as a creative engine helps us appreciate the delicate balance that sustains complexity amid constant change. It invites us to honor the subtle flow of energy and matter that continually gives rise to new forms, new possibilities, and new horizons. Ultimately, embracing entropy's power can deepen our connection to the universe, reminding us that we are participants in an ongoing dance of creation that has been unfolding since the dawn of time.